This screencast is from the textbook Motion, Forces, and Energy. This is page 43 and 44 that I'm going to be reading, and this deals with the units of force. Make sure you have your B1 worksheet because you need to finish and include some of this information on there. So let's start with units of force. Force is measured in newtons. It's abbreviated with a capital N because the SI, which is System International Unit for mass, is the kilogram, and acceleration has units of meters per second squared. 1 newton also is equal to 1 kilogram meters per second squared. We're not going to calculate a force in newtons from the equation shown on the prior page because we didn't read the prior page. It wasn't included in it. So we're going to focus now on gravity as one of the forces. One force that you are familiar with is gravity. Whether you're coasting down a hill on a bike or a skateboard or jumping into a pool, gravity is at work pulling you downward. Gravity also is the force that causes Earth to orbit the Sun and the Moon to orbit Earth. What is gravity? We are down here now. The force of gravity exists between any two objects that have mass. Gravity always is attracted and pulls objects toward each other. A gravitational attraction exists between you and every object in the universe that has mass. However, the force of gravity depends on the mass of the objects and the distance between them. The gravitational force becomes weaker the farther apart the objects are and also decreases as the masses of the objects involved decrease. For example, there is a gravitational force between you and the Sun and you and Earth. The Sun is much more massive than Earth, but is so far away that the gravitational force between you and the Sun is too weak to notice. Only Earth has enough mass and is close enough to exert a noticeable gravitational force on you. The force of gravity between you and Earth is about 1,650 times greater than between you and the Sun. The next section is about weight. The force of gravity causes all objects near Earth's surfaces to fall with an acceleration of 9.8 meters per second. By Newton's second law, the gravitational force on any object near Earth's surfaces is force equals ma, which is mass times acceleration, which is equal to m times 9.8 meters per second squared. This gravitational force also is called the weight of the object. Your weight on Earth is the gravitational force between you and Earth. Your weight would change if you were standing on a different planet than Earth, as shown in Table 1, which is right over here. Your weight on a different planet is the gravitational force between you and the planet. Now we're going to scroll down and talk about weight and mass. Some of this we have already talked about in class, but it's a refresher. Weight and mass. Weight and mass are different. Weight is a force just like the push of your hand is a force and is measured in newtons. When you stand on a bathroom scale, you are measuring the pull of Earth's gravity, a force. However, mass is the amount of matter in an object and doesn't depend on location. A book with a mass of 1 kilogram has a mass of 1 kilogram on Earth or on Mars. However, the weight of the book would be different on Earth and Mars. The two planets would exert a different gravitational force on the book. Now we're going to look at Newton's second law. I know this isn't pertaining into this matrix where you're focusing on just the forces, but forces come into Newton's second law and you will be learning that in the next matrix, so it's good to be familiar with some of this. How does Newton's second law determine how an object moves when acted upon by forces? The second law tells how to calculate the acceleration of an object if its mass and the forces acting on it are known. You may remember that the motion of an object can be described by its velocity. The velocity tells how fast an object is moving and in what direction. Acceleration tells how velocity changes. If the acceleration of an object is known, then the change in velocity can be determined. The next section is speeding up. Think about a soccer ball sitting on the ground. If you kick the ball, it starts moving. You exert a force on the ball, and the ball accelerates only while your foot is in contact with the ball. If you look back at all the examples of objects speeding up, you'll notice that something is pushing or pulling the object in the direction it is moving, as in figure 8, which is up here. The direction of the push or pull is the direction of the force. It is also in the direction of the acceleration. And this is all you need for this assignment, so I'm going to stop here. Thanks.